Hey guys, welcome back. In this video, we are going to solve this very interesting question which I found on Reddit. And this question is regarding the maximizing of the area and minimizing of the perimeter, which also involve checking the local maxima and local minima of the function. The question says that an equestrian club wants to construct a corral next to the barn using the side of the barn. They have 300 feet of fencing. Find the dimensions that gives the maximum area. As you can see that this is the barn, right? And corral. And they want to fence this corral with the fence of 300 feet. Okay. And it also says that this side is y, right? And here this side is x, right? But here, as this 60 feet is already been covered by this barn, they need not have to cover this 60 feet. Only this portion they need to fence it. So one side they only have to fence x minus 60 feet of the portion, but here they need to fence it fully, and these two also they need to fence it. So first we have to find the perimeter so that we can generate the function of the perimeter in terms of x and y, and then we have to check it using the second derivative test. Okay, so now we have that perimeter. The perimeter is given by adding up all the sides. And before that, one thing is that in the 2D shape, the circle is the most efficient shape. Therefore, any shape, be it a rectangle or square or pentagon or hexagon, if it resembles similar to a circle, then it will have the maximum efficiency. And here efficiency means that the shape will have the least perimeter and maximum area. So among these, this square resembles more like circle than the rectangle. The square is more efficient than the rectangle, and this hexagon resembles more like a circle than the rectangle. So this hexagon will have the greatest efficiency among these three shapes. Okay, so here, since the barn is rectangular shape, we are trying to optimize this rectangle such that it will change to square, so that it will cover the maximum area and it will require the minimum fencing, which means the least perimeter. Okay, such that when we optimize, we have to make sure that x is equals to y, as the square has the equal sides and square is the most efficient among the rectangles. It's very interesting. Okay, now first calculating the perimeter, we will have that, see here, y plus x, this x plus x minus 60 equals to 300, because they have 300 feet of fencing. So simplifying this, we'll get 2y plus 2x equals to 360, which implies just divide by 2 on both sides because they have common factor. So x plus y equals to 180, and make like y equals to 180 minus x. Let this be equation 1. Now what we have to do is we have to maximize the area such that when we get the critical points of the function, like x equal to a and x equal to b, like that, when we check whether it has a local maxima or minima of this critical point by finding the second derivative of the function, we have to prove that the area is maximum. Okay, now we have that area is what? Area is x times y. So here we have x, substitute this here, we will get 180 minus x, which equals to 180x minus x squared. So this is the area function. Okay, now we have to use this function to optimize such that it will have the maximum area, minimum perimeter, and by finding this x value, which is the critical point of the function, we can substitute this x value in the second derivative to find out whether it has the maxima or minima or inflection point. Okay, we have that. To maximize this, we have to equate the first derivative of this function to 0, right? So we have dA, this area, over dx equal to 0. We are maximizing this. We will get what? 180 minus 2x equals to 0, and we will get x equals to 90 feet. So this is one of the critical point. Now we have to check that at x equals to 90 feet, the rectangle will have the maximum area. And we have to also find the y, another dimension, because if we have x, then we can easily find the y value from this function, right? Now to check this, whether when x equals to 90 feet, whether the area will be maximum or minimum, we have to find the second derivative of the function. We have to do a derivative test, and I will tell you something, and we have 3 conditions. Okay, for example, see here. So if this is the critical point, which is x equal to a, here it is 90. Okay, what is the slope here? The slope is exactly 0, which is dy upon dx when x equal to a is 0. So this is the main reason why we are equating this to 0 at first. Okay, but if this has the maximum, which is, this is the local maxima, right? If you can see this, for example, if we have function like, then these are the local maximas, right? These are the local maximas, and these are the local minimas, right? So by using this is the local maxima. So what happens is, as the point reaches this x equals to a, from here the slope decreases, right? So it enters to a negative side. So if we take another derivative from here to find the slope from this point near to this point, that means we are equating the second derivative of the function. Okay, so from here, if it has a local maxima, what happens is, as soon as it passes the point x equal to a, the slope decreases, which means the slope turns to negative, which means when x equals to a, as soon as it hits the a and find the slope becomes negative, which means this second derivative is less than 0, right? Because it turns to negative. And similar to this, if this has the critical point x equals to a, what happens here? At x equals to a, the first derivative, the slope at x equals to a equals to 0. But as soon as it passes x equal to a, the slope increases, right? Which means the slope has a positive sign. So we are finding the second derivative now, because it is already first derivative here. But from here, when x equals to a, then the slope becomes positive, which means it becomes 0, right? But if you consider here this point, okay, x equals to a, what happens here is, the initial derivative of the function when x equals to a is 0. Even if it passes x equals to a, the slope doesn't change, the slope still remains 0, right? Which means this second derivative at x equals to a is 0, which means that there is no change in the slope even after passing the critical point. So this kind of condition is called the inflection point or saddle point, which means we don't know whether this curve is decreasing or increasing at x equals to a. So this is how we test whether this function will have the maxima or local maxima or local minima or inflection point at any critical point. Okay, so like this, if we want to increase the area, that means our second derivative should be less than 0, which means it should be negative. Okay, I hope you have understood this. Now we have to find the second derivative of this function as d squared a upon dx squared at x equals to 90 is how much? It is here 180 minus 2x is dy upon dx, right? So it will become negative 2 only. So what is it? It is less than 0, which means that after it passes x equals to 90, the slope becomes negative, which means the graph hits the maximum at x equals to 90 and then decreases, means the graph has the local maxima, which means that at x equals to 90 the area will be maximum. Okay, therefore we have proved that if we choose x equals to 90 feet, then you will get the maximum area and you will get the minimum perimeter. Okay, now we agree that one dimension should be 90 feet. What should be the other dimensions? Now other dimensions can be easily found by this relation. Now what is the relation? The relation is y equals to 180 minus x, which implies y equals to 180 minus 90, which is 90 feet. So see here, I told you that among the rectangles, the square is the most efficient rectangle. Two sides should be equal, which means x equals to y, which is 90 feet. And we have also proved geometrically that when we choose x equals to y equals to 90 feet, then we'll have the maximum area. Now let's cross check that whether when we choose x equals to y equals to 90 feet, we are able to cover this by 300 feet of fencing or not. Okay, so for this we have that 2y plus 2x minus 60 equals to 300, right? So by substituting x equals to y equals to 90, we will get 290 plus 290 minus 60 equals to 300, which is 300. 360 minus 60 equals to 300, which is 300. Okay, which means that these sides x equals to y equals to 90 feet is valid. Okay, now the final thing is, the question says find the dimensions that give the maximum area. So now the dimension is x equals to y equals to 90 feet, and if you compute the area, this area will be the greatest. Okay, area equals to x squared, because you can say x equals to y, right? So we will get 90 squared, which is 8100 feet squared. Okay, answer is x equals to y equals to 90 feet, and we have verified this answer by using the second derivative test. I hope you have enjoyed this video and understood this question.